Welcome to another coding tutorial, and in today's video we're going to be doing some music visualization while learning the basics of fast Fourier transform. The song that we're going to visualize is called Veil by a talented musician and a friend, Etienne Mason, and I'm going to link his stuff down below so you can check it out. This video is part of my sound mini series where we go through the different classes within the P5 sound library. Specifically within this video, we're going to dive into another class called FFT or Fast Fourier Transform. But before we do that, I would like to recap a few concepts so that we're on the same page. The two key concepts that I want you to keep in mind, one is amplitude and two is frequency. Amplitude is the volume, while frequency is the pitch or how low or how high the note is. And knowing just these two key concepts and a few of the classes within the P5 sound library, you can make pretty cool sketches already, and I have a few examples on that. But knowing the FFT class will allow you to add a little bit of an additional feature to your sketch, which will make it a little bit more interesting. So, what is FFT? FFT stands for Fast Fourier Transform, and don't let that name scares you because it sounds a little bit scary. If you look at this virtual oscilloscope, which is the device that allows us to graph the sound wave, and as you can see here, the sound is based on my voice and it is taken by the computer's microphone. And you can see if I were to freeze the live input, hello, the shape of this sound wave doesn't look like a pure sine wave, and that is because the sound of my voice is not one specific pitch or frequency. It is actually a bunch of different frequencies added together, and that is exactly what you see here. And the kind of graph that you see here is actually called a time domain graph, where the x-axis represents the time and the y-axis represents the amplitude or the volume of all of these added frequency. And what FFT does through some mathematical equations is just separating these set of frequencies into distinct frequencies at a specific volume or amplitude. And it is going to be represented in a different kind of graph called a frequency domain graph, where the x-axis represents frequency and the y-axis represents the amplitude specific to that frequency. And now that you understand the basics of FFT and also the differences between the time domain graph and the frequency domain graph, let's try to implement it in our P5 sketch. Alright, so we're going to start by uploading the song. So you need to come to this arrow here, click the plus sign, and then click upload file. And now you want to drag and drop your song file in here. And once your file is uploaded, what you want to do is first we're going to declare a variable, let's call it song, and then we're going to write a function called preload, which will allow us to preload the song onto the sketch before we even call function and draw. So we're going to set song to be equals to another function called load sound, and inside here we're going to put in the name of our file, in my case veil.mp3, and don't forget to put it inside a quotation mark. So veil.mp3, and then I'm going to just click run just to make sure that everything is running properly. And it is, so that's good. And then inside setup, I'm going to play the song, and all I need to do is just put in the name of this variable, song, and play, and let's click run. All right, so you do hear the song is being played right now. Perfect. Next, I'm going to create a new FFT object. So I'm going to start by creating a variable called FFT, and then inside setup, we're going to set FFT to be equals to new p5.fft. And then inside here, we can put in two arguments. The first one is for smoothing, and the second one is for bins. So smoothing in the context of FFT is a technique to reduce noise from the sound signal. And it ranges between a value of 0 and 1, where the default value is at 0.8. And the second argument is called bins, and bins or a frequency bin is a way for us to cut up the continuous range of frequencies that we want to analyze into discrete sets of frequencies. And the higher the number of bins, the higher the number of set of frequencies that we're going to be getting as an output of the FFT object. And the value of bins must be a power of 2 between 16 and 1024, where the default value is 1024. So I'm going to also declare these two variables, smoothing, and I'm going to set smoothing to the default value of 0.8, but I'm going to set bins to 512, so smaller than the default value. Then I'm gonna put in smoothing here and bins here. All right, and now inside draw, we're gonna be using two methods. The first one is called waveform, and then the second one is called analyze. And what we're gonna do is that we're gonna be graphing out the two kind of domains, the time domain graphs and the frequency domain graph. So let's start with the time domain graph. So what I'm gonna do is I'm going to create an array called waveform. And then inside draw here, we're going to set waveform to be equals to FFT dot the method called waveform. And then I'm going to print out what waveform is. All right. All right, you can hear the song is playing and you can see the values here. All right, you see the values are changing when there's that drum sound, right? So let's look at this. So you can see that this is a 1D array with the size of 512, which is the size of our bin, right? And the values is between negative 0.24 here, and it's still negative. Let's see. And then there's some positive values. So the range of this waveform method actually is between -1 and 1. And it is of the size of whatever you set as the bin size. So how about we graph it out? I'm going to use a for loop that goes from I equals to 0 to I less than waveform dot length, which is 512 in this case, I plus plus. And how about we just draw an ellipse, right? And the x location will be based on I here, which goes from 0 to waveform.length minus 1, and then y. And then I'm going to set a size of 1 and 1. So what is y going to be? So y is going to be waveform of I, right? And let's try that. All right, so first we want to move this down here. So I'm going to also add height divided by 2. All right, so even though you heard that drumming sound, you don't see anything, and that is because why? It is because this waveform values are between -1 and 1, so we actually want to map it, right? Between -1 and 1 to how about, let's set a radius. Let's do -r and r, and I'm going to set the radius at, how about 100? Let's try that. You can see it moving a bit. Nice. So it looks like what you saw in the oscilloscope earlier, right? So actually also, instead of setting the canvas size to be 400 by 400, I actually want it to be bins, comma bins, so that we actually see the whole range between 0 to 511. Great. So now we have what is called the time domain graph, right? But what we actually want to do is that we want to be able to analyze or see the distinct frequencies and its corresponding amplitude. So we're going to be graphing the frequency domain using the FFT.analyze method. So I'm going to create another array called spectrum. And we're going to set spectrum here. Spectrum is going to be FFT.analyze. And I'm going to also comment out this. And also let's print out spectrum first before we graph anything. All right, so you notice that the size of this 1D array is also 512, but the values are actually higher, right? And as you can hear this, when the drum is played, the values seem to be a little bit higher, but we'll graph it so you can actually visualize it. So let me just show you real quick. So as you can see here, the value is actually ranging between 0 and 255, right? And it has a total of 512 bins. So the continuous series of frequencies are cut up into 512 set of discrete frequencies. All right, so now we're going to do the same thing, which is setting a for loop between I equals to 0 to I less than spectrum dot length I plus plus. And right now, what we want to draw is actually how about a set of lines to visualize each of the frequency bin. So line of I, comma, Y, and then I, comma, actually it's going to be 0 to Y. And then what is Y going to be? So let Y to be equals to spectrum of I, and we also want to map it, right? We want to map it between 0 and 255 to 0 and height. All right, and you can see here the lower set of frequencies has a higher amplitude at the beginning. It's very high when the drum is played, right? But the higher the pitch, you can see when there is that sound, whatever that is called. All right, but I want to change one thing before we move on, which is I want this to be right side up, and all we need to do really is instead of putting 0 here, we can do height, and we can do height minus Y here, and now it is right side up. Perfect. All right, and then one last method that I want to show you is actually called get energy. So I'm going to set a variable called let vol for volume, and we're going to set it to FFT.getEnergy. And we're going to put a range of frequencies as the arguments in this. So I'm going to put in frequency of 20 and 140, and that is because I want to get the volume or the amplitude of the frequency that ranges between 20 and 140. So let's try to print out volume. So you can see that the number is also between 0 and 255. And right now it is around 90. But when the drum is played, and the drum is within the range of frequencies between 20 and 140, you can see that the range of frequency goes up to over 240. And why do I want to do this? This is just an additional feature that we can play around with, right? We pick out a set of frequencies that we want to visualize, and when the volume hits a certain threshold, then we can maybe change a different color or something like that. So how about we do just that? So if we write a conditional statement that says if volume is greater than, how about 250, then set the stroke color to red, and then else, then we're going to keep it as black. So right now it is below 250, right, the volume. All right, so you can see a little bit of the red coming here. So the threshold of 250 or whatever value that makes sense to the song that you visualize, you can change, right? Perfect. So now that you saw the ways to use the different methods within the P5 FFT class, now let's make the final result that you saw at the beginning of the video. All right, so because we're going to be drawing a set of cubes, first we need to change the mode to WebGL, and you can do that by just putting the third argument within the create canvas function here. And then now what I'm going to do is I'm going to draw a box, and I'm going to just write the function called box and put in a size of how about 50. Two things that I want you to notice here. The first thing is that the box is drawn in the middle of the canvas, which is different than the 2D mode where the origin is at the top left corner of the canvas, right? The second thing that I want you to notice is that I only put in this one argument, which is the size of the box, right? I can put in more arguments, but that is going to only impact the dimension of the box. But how do we actually move the box around? I'm going to change it to 50 again because I want all of the dimensions to be the same. But the way that we actually move the box around is by using a translate function. and let's say we want to translate it by 50 to the right. So we can just do 50, 0, right? So it was here before, and then now it's here. And that is how we're going to be setting the location of each of the boxes. And before we move forward, I'm going to put in a function called orbit control, which allows us to use the mouse to basically control the view of this sketch. Great. Now that we have one box, what if I want to draw another box to the right of this box? You would think that we just do what we did before, right? Translate by 50, 0, and then draw another box. And you would be right. Now we have two boxes. But what if we want one more box to the right of this second box? If I do translate, and we want to translate by, how about 100, 0, right? Because this is 50, this should be 100, and then draw one more box. Oh, you can see that there is a gap here. Why is that? And that is because when we use any transformation functions, we need to think about the origin point at which things are being translated, right? Or things are being transformed. In this case, once we translate the origin point from 0, 0 here to 50, 0, which is here, now that is the new origin point. So now this box is being translated 100 to the right from this new origin, right? So 50, then 100, and that's why there's a gap between these two boxes. So to not have this, or to return the origin point to the middle of the canvas here before we call the next translate function, what we need to do is we need to put in two functions, push and pop. So we can put push here, and push saves this transformation, and then pop returns it back to the origin point, which is this center here. So if I do this, then now there's no gap, right? And now instead of actually just calling the same functions over and over again, so as you can see here, basically this is translate of 0, 0, right? And this one is translate 50, 0. This one is translate 100, 0. So what we want to do is, how about we write a for loop that goes from let I equals to 0 to I less than, let's do 3, I plus plus, and I'm going to put in this set of functions in here. And instead of translating it by 50, 0, we want to do it translate by 50 times I, right? And also, how about we set the size to be 50, and we do I times size here, then this will be size. Instead of 3 here, let's do num, and set num to be equals to 3. And we get the same thing. And now what I want to do also is to do it in the vertical direction, the y direction, and also the z direction. So we need an additional for loop. So for let j equals to 0, j less than num, j plus plus, and put all of this inside here, and make sure that instead of 0 here, we want to do j times size, right? All right, and then the last one, for let k equals to 0, k less than num, k plus plus, and also put everything inside here, and make sure that we put in the third argument into this translate function, k times size. All right, but this box here is the first box where ij and k equals to 0, right? So let's do it. Fill of 255, and then I want to just show you that it is this box that is the first one. So let's do size, and oh, actually it's this one. All right, so we actually want the middle box, the one that is in the middle of all of these cubes, to be in the middle of the canvas. So we need to do some translation of the entire big cube here. So we're gonna do translate, and how much are we going to translate? instead of doing fill this, I'm going to actually do no fill. Oh, here. All right. So we want to move it by the number of num here, which is 3 divided by 2, right, to the left. So what if we translate it by num divided by 2 times size, and we need to also to the left, so it's negative, right? And then comma 0, comma 0. All right, and you can see that this red one is also moved. So what we want to do just for this case is also put in push here and pop here. Nope, it has to be before translate, right, before the transformation function. All right, so as you can see here, I moved to the left a little bit too much. By how much? By size divided by 2. All right, and we want to do the same thing for the y and the z direction. So actually, instead of putting it like this out here, I'm going to set a variable called offset and set it equals to this, and then put in offset here, and then offset for the y direction. Great, but then the z direction is also need to be moved by this amount. Perfect. Great. So now that we have this, we can delete this box here, and we don't need push and pop anymore, right? Because we don't have that red box. Perfect. And then now you can change the size to whatever you want. So let's do size of 15, and then the number will be 10 by 10 by 10. Nice. And I want to also set the size to be a little bit smaller than each of the spacing between each of the boxes. So there's going to be a slight gap between each one of them. Can you see it? Also, orbit control allows you to zoom in and zoom out as well. Great. Now what I'm going to do is I'm going to create an array called grid, and grid basically is going to store a value between 0 and 1, where that is going to be the value that I'm going to use to color the boxes. And inside setup, we're going to create this array, which is going to be a 3D array. So we will need this nested for loop, and inside this one, inside the most outer for loop, we're going to set grid of I to be equals to an empty 1D array, and then inside this second one, grid of I and j will be another set of empty arrays. But then the last one here, we're going to set it equals to 1. How about we set everything to 1 for now? And then inside here, we're going to use the values inside that grid 3D arrays to set the colors. So we're going to say if grid of I, j, and k equals to 1, then fill the color red, and else fill it with white. And as you might have expected, everything is red, and that is because I have set the value inside this grid to be 1. So how about we use a random function to randomize the value? So random of 2. So random of 2 outputs a value between 0 and 1.99999, but we actually want the value between just either 0 or 1. So we can use a function called floor, and floor will get us an integer that is closest to that decimal value. So between 0 and 1.999, we're going to get a value of 0 or 1. And ta-da! So we get a random set of colors. Perfect. Now, we're going to integrate what we learned in the previous sketch of how to use the FFT class in here. So what we want to do is that we want to color the cubes based on the frequencies of the song. And I want the innermost cube or the most center cubes to be of the lowest frequency, and the outermost cubes, which are here, will be the highest frequency. So let's start by uploading the sound file. And then we're gonna call the preload function and set song to a function called load sound, and the file is called veil.mp3. All right, and then we're going to also create an FFT object, right? And then inside setup, FFT is going to be a new FFT object of smoothing, and I'm actually going to set bins this time to be 1024. Actually, I'm going to leave it like this because the default value for smoothing is 0.8 and for bins is 1024. Perfect. And then inside draw, we're going to first actually create an array called spectrum, and then spectrum is going to be FFT dot analyze, right? And it's going to output a value between 0 and 255 based on the frequencies. But actually the one thing that we need to do before we can use the value from the spectrum array is that we need to be able to map the location of the frequencies, the lowest frequencies, to the innermost cube, which is the center of this big cube, and then the higher frequencies to be at the edges of these big cubes. So how do we do that? First, we're going to create another array, and let's call it distant from center, right? And then inside here, we're going to create a variable called distance, and we're going to find a distance between the center of each of these small cubes to the center of the big cube, or essentially the origin point of the sketch, right? So I can use a function called dist, and it's going to be between a value of x, y, and z, and 0, 0, 0. So let's set what x, y, and z are. So x will be equals to I times size, y will be equals to j times size, and z will be equals to k times size. And if I just do it this way, x, y, and z values will actually start in the middle of the canvas because I times size, j times size, and k times size is 0, 0, 0. So what we want to do is that we want to set this cube here to be the very first one. So we also need to use the same offset that we used previously, which is size divided by 2 minus num divided by 2 times size. And we're going to add this by offset. And then we're going to push these values inside the distance from center array. So we're gonna put in an object of x, y, z, and distance. So we can do this and use the curly bracket here. All right, so how about we print out dist from center? FFT is not defined. Oh, p5 dot, don't forget that. Okay, so we have a total of 1,000 objects, which is what we expected, right? And let's look at each of these. So, oh, instead of x, y, and z, what I want to put in is actually I, j, and k, because I want the index value. So let's try that again. All right, so if we come here to the very beginning here, you can see that the first one has I, j, and k to be 0, 0, 0, and then whatever the distance is, right? And then the next one is 0, 0, 1, the next one is 0, 0, 2. So the value inside this from center array is sorted based on the values of the index. But what we want to do is that we want to actually sort it by the value of the distance here. So I want the smallest distance to be first inside this distance from center array. And we can do that by using the sorting method inside JavaScript. So we're going to come here, which is outside of the 3D arrays here. And we're going to do this from center.sort, and then we can tell it how to sort it. So how about I write a function that say compare distances, and we're going to put in two arguments, two objects a and b, and we're going to return a.distance minus b.distance. So it's comparing the two values that we're going to sort, and then we can just put in this inside here, compare distances. And then now let's try to print this from center again. All right, so you can see ij and k now is 444, and then the distance is 12.99. This one is 12.99. This one is still 12.99. This one is 24.87 and 32.69. So you can see that it is sorted from the smallest distance from the center to the biggest distance. So now what we can do is that we have the spectrum array that has the amplitude values of the set of frequencies, right, from low to high, and then we can set that to the cube locations based on the distance they are from the center of the cubes. All right, so what we want to do now is that we want to go through the entire 1D array of the size of, actually just the size of the cubes, right, which is I less than, how about we create a variable called total cubes to be num times num times num. And this, the num right here is 10, right? 10 times 10 times 10, which is 1,000. And it's smaller than the number of bins that we have, which is fine. It would not be fine if it is greater, actually. So we're going to put in total cubes here, and then I++. And then we're going to get a position. So pos will be equals to distance from center of I, right? And this, the first three values inside this object is the I, J, and K index values, right? And then we're going to set the color. Let's call it C, and C will be spectrum of I. And then now we're going to set grid at location of post.I, right? Post.j and post.k to be equals to C. And now the grid values is equals to C, and then now we need to, instead of doing this, we're going to fill it with grid of I, J, and K. All right, that was a lot, but let's try it. Oh, we never actually played the song. So let's do song.play. You can kind of see something inside, can you? Let's see. All right, but why is everything black? Why is everything black? And that is because most of the values are actually at 0, right? The ones that are not actually have high volumes, which are the high frequencies. So what we want to do is actually say if grid of I, J, and K is greater than, let's do minimum, right? Then we will put in this color, and else how about we do no fill? And what is minimum here, right? In this case, minimum is 0. So we can set let min to be equals to 0, and yeah, so this should be fine. So you can see that it's black. Alright, so you can kind of see inside. But what we can do also is, right now spectrum ranges between 0 and 255. What if we map it between 0 and 255 to min and 255? And we can actually change the value of min here. So we can change it to, let's say, 150. And instead of doing it in grayscale color, what if we do 0 and 200 to give it the purple-ish color that we see? All right. Cool. All right. We're almost there. The last thing that we want to do is that we want to get that volume, right? The get energy method. So let's do that. So this get energy method actually needs to come after the analyze method. And we're going to set volume to be equals to FFT.getEnergy. And also let's set it between frequencies of 20 and 140. And this range you can change to whatever matches your song, right? And I'm going to say if volume is greater than 240, then we will do the stroke color to be a yellow color. So 255, 255, 0. And I actually want the transparency to be smaller. Let's do at 20. Then else, we will color it black with the same transparency of 20. All right. Let's see. Cool. You see that like flashing light? It gives it like a pretty cool effect. I really like it. So this is my take on this FFT class to visualize a song by my friend Etienne Mason. So check out his stuff down below and yeah, give this one a try.